Okay, let's get going. Let me just start with a few announcements. Homework due on Friday. And there'll be, I'll assign a new homework on Friday, and it's going to be due either Wednesday before Thanksgiving, either I make it a short one that's due on Wednesday before Thanksgiving, or make it due Monday after Thanksgiving. Assignment on Friday. It's the last one for the semester. And final December 5th, 9:30 to 11. Just so that I can get a quick show of hand, how many people would rather have the homework be due Wednesday before Thanksgiving instead of Monday after? Raise your hands. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. How many people would rather have the homework due Monday after Thanksgiving? 1, 2, 3, 4. So the majority, there's more. And how many people just don't care? 1, 2, 3. Okay. I'll keep that in mind, and we'll go with that. So are there any questions or comments before I get going? What we talked about last time had to do with how we can use DFT to do linear filtering. In particular, what we found out was that if you have two, let's say, endpoint sequences, and you want to convolve them with each other, if you take the endpoint DFT of each one of them, multiply the two things together, and then take inverse endpoint DFT, the answer that you get is a circular convolution and not linear convolution. On the other hand, in fact, that's sort of obvious because a linear convolution of two endpoint sequences is a 2n minus 1 point sequence and not just an endpoint sequence. So if you want to end up with a 2n minus 1 point sequence, then you go to pad those sequences with n minus 1 zeros, take 2n minus 1 point DFTs of each, multiply the 2n minus 1 point DFTs, and then take inverse 2n minus 1 point DFTs, and that way you get the right answer. And we proved that by relating DFT to DTFT, we've proved that that's indeed the correct way of doing things. So here we've got a computational tool, DFT, in order to come up with a way of doing linear convolutions on the basic signal processing operations, and used always a lot of times in LTI type systems. What I'm going to talk about today is how to use DFT for filtering infinitely long sequences. I'll spend very little time, maybe 10 minutes or 15 minutes on that, and then I'll move on to yet another transform, discrete cosine transform, which is used quite a bit in image processing. Relate that to DFT and talk a little bit about the compaction properties of discrete cosine transform. I think that'll be sort of most of today's lecture. The topic we'll cover after DFT is FFT. And I will talk about FFT on Friday and also possibly on Wednesday of next week. And you'll end up doing a MATLAB assignment on FFT just so that you can get a feel of what's going on. And that just about wraps up the core content of the course that I want you to be responsible for the exam. And then the remaining 1 or 2 lectures, I'll probably talk a little bit about either filter banks or an application like speech. and show the use of DFT in speech coding and audio coding. Since a lot of you, I assume you're young and interested in MP3, maybe you want to know how MP3 works under the hood. Get an understanding of what the building blocks are. Okay, so any questions or comments? Technically, yeah. That's just
so the exam covers everything except for the last 2 lectures?
I'll tell you when we get closer. It covers through FFT. I don't know the pace of the lectures. I can only tell you what content it covers. So it covers today's lecture all the way through when we finish FFT. And then beyond FFT will not be covered in the exam. Okay? And again, I've also made sure that every topic that's covered in the exam, I want to make sure you do a homework on. It's really hard for you to appreciate this, but really the only way to learn the material is to do the homework and to do it yourself. That's the only way you figure out whether you you might go through the lectures and say, oh yeah, I understood everything. Yeah, everything is good. But then when you go to the homework, you have to read the book again, watch the lectures again, and you come to a new level of understanding that maybe it's not achievable by just watching videos and watching lectures. So think of homeworks as a tool to help you digest the material in the class. Okay, any other questions or comments? All right, so let's talk about using DFT for filtering infinitely long sequences. So let's say I start with X of n, and I apply it to an FIR. I want to filter it with an FIR filter, and H of n, and X of n is very long. Perhaps it's infinitely long. For example, suppose that I'm talking on the phone, and I talk for 5 minutes. And suppose somebody has to do some sort of a linear filtering of my voice, maybe to remove some high frequencies in order to fit in some bandwidth, or remove noise or something like that. They can't wait for me to talk for 5 minutes and then take the 5-minute DFT of my voice and then filter it and then take inverse DFT and then send that signal, let's say, to my mom or something. It wouldn't be a conversation at that point. The signal has to get filtered as I talk. Okay? So one way of doing it is to do this convolution as we talk. But suppose that you wanted to do it via DFT, it's a more computationally efficient way of doing it. Then the question is, how do you do it? Okay. In a lot of applications, delay is very important. Communication applications is very important. Conferencing applications. The telephone industry has its own set of specifications. The delay, let's say, between New York and Los Angeles, the 2 furthest east and west point in this country, when you talk on the phone, cannot exceed 150 milliseconds. Otherwise, the nature of the communication is not conversational. It's more, you lecture, and then you stop, somebody else lectures, you listen. It's more like that. So suppose then you have an FIR filter with a small number of taps here. And so this signal, X of n, just sort of goes on forever. As a function of n, it's just been going on for a long, long time. And so the question is, how can we use DFT in order to help us do this filtering of this infinitely long sequence? Okay. So the property that we're going to be exploiting to do that is really the linearity property of convolution. So we're going to exploit linearity property of convolution in the following sense, that if I have x1 of n plus x2 of n, both convolved with h, it's the same thing as x1 convolved with h plus x2 convolved with h. That's what I mean by linearity property. And here's 2 ways I can exploit this linearity property in order to filter this infinitely long sequence. One way of doing it is to say, okay, I have this very long sequence. I'm going to chop it into segments of L points. L, 2L, 3L, 4L, 5L, etc. And I'm going to process each segment, and then convolve, process, I mean convolve. So convolve this segment with H, convolve this segment with H, and then convolve this segment with H, and convolve this segment with H, and then add them up with each other. Okay? So for the sake of argument, suppose that this FIR filter has a small number of taps. Let's say it's got P taps. Okay? So if I want to convolve the first, let me refer to these as chunks. If I want to convolve the first chunk, the first L point chunk with a P point impulse response, what's the length or what's the region of support of the convolution? L plus P minus 1. So I get something that looks like this. It goes from 0 to all the way L plus P minus 1. So this is, I call this x1, x2, x3, x4, x5. So this is just x1 convolved with H. And what happens if I convolve this chunk, this second chunk, with H? Then I get another L plus P minus 1 point, but what would be the indices of that L plus P minus 1? It starts from here, and it lasts all the way here. It starts from L, and it ends at 2L plus P minus 1. That's x2 convolved with H. And what happens if I convolve x3 with H? I get something like that. I get something that starts at 2L, and it ends at 3L plus P minus 1. So here, I've decomposed this into chunks. I've convolved each chunk with H, and then I add these things up together. Okay, so when I add things together, the answer from 0 all the way to L is just this copied from this chunk. Gets copied over here. Okay, and then the answer from L, for example, to L plus P minus 1 is the summation of this chunk, the summation of this plus that. So it would be these two things added here. And then the answer from L plus P minus 1 to 2L is just this chunk, just replicated here. Okay? So these two things get added. So on and on and on. So I'm essentially exploiting the linearity property of convolution to just do that. And this technique is called overlap and add, or overlap add. Okay? Like a comedy here. No matter what you fix, okay. We got everything in place now. Okay, so this technique here is called overlap add. Okay, and the basic ideas and the steps can be summarized like this. You segment the infinitely long sequence into L non-overlapping blocks or chunks. And then what do you do after that? Then you convolve each chunk with H. Okay, so that's step 1. Step 2, you convolve each chunk with H, which is a p-point sequence, and then you get L plus P minus 1 new points, and you have to position those new points the right way, and then you add up all the convolutions to get the answer. Okay? So that's it. That's the whole idea behind what's called overlap add. And as one of you mentioned, I guess I'll talk about this at the closing of DFT when I'm all done with DFT. One of you last time mentioned is that should we always use DFT to be doing convolution? So, and my answer to him was that, well, there's fast algorithms called FFT to compute DFT, and therefore, yeah, you should, only if the length of the sequences that you deal with or the length of DFTs you deal with are large enough. If they're not, then it's cheaper and it's less computation to do convolution. In particular, what are besides? I mean, this notion of complexity that we all have in our heads is perhaps a rather old-fashioned one. Besides counting the number of operations, how many CPU cycles it took to do an operation, to do a convolution, what is sort of another important measure? What's another important thing people care about? Let's say I was going to implement convolution, and I'm trying to decide, shall I use the straightforward convolution, like, x of k, h of n minus k, summation? Can I just do the direct computation, or shall I go through FFTs and DFT? Granted, I didn't talk about FFT, so you don't know what it's all about. But for those of you who do know about FFT, besides counting, let's say I already know all the parameters. I know that I'm going to be dividing my sequence into 1,000-point chunks, so I can either take 1,000-point DFTs and inverse DFTs, or I can be doing convolutions, straightforward convolutions directly. Besides counting the number of operations, and which is exactly what's in your homework, for example, and computing to see which way has fewer operation cycles, what are the other important factors? Pardon? Memory usage, okay. And what do we exactly mean by that? The runtime memory you're talking about. So when you write a code, there's a thing called runtime memory. How much RAM does it need for this C code to run? What else is important? Yeah, it is maybe at the lower level, but something that you're all forgetting that's very important. I think Kevin and Alan should at least hit it. Not that I wanted to put you guys on spot. What's the thing we all worry about? Like, let's say you're downloading an application over the air onto your cell phone, or that's the thing I worry a lot about. Okay, or downloading things on the internet has become trivial because it's high speed. Exactly. This application size, the size of the executable. How many megabytes or bytes or kilobytes is the size of the application? And why is that important? Because its devices have limited ROM size for people to run applications on or to run programs on. So whereas the convolution code is exactly 5 lines. I mean, I bet you it's no more than 5 or 10 lines, right? What is it? It's just a do loop. 4 k equals 0 to infinity, multiply h of k, x of n minus k, and add up. And that's it. It's very, very simple. You can just say it in one sentence. You can't quite say that about DFT. You've got to have an FFT program. And an FFT program is a lot more than 5 lines, I can assure you. So the size of the application sort of grows. So what technique you end up using has a lot to do with what your constraints are. If you're dealing with image processing or 2D or 3D signals, then it really does pay off to use FFT because I won't talk about it in this class, but when you go from regular when you use FFT, you end up having n log n type complexity. When you use FFT in 2 dimensions, the savings are even higher, and the 3 dimensions even higher as compared to doing convolution only. So which approach you end up doing, whether you want to use DFT or whether you want to use straightforward convolution, is highly application dependent. Okay. Very good. So, so that's really overlap add. I'd like to comment, talk about one other. Any questions on this before I keep going, or any question on this discussion we just had? So, okay. So, just one last comment on that. So, one application where the size of the application is very important is cell phone industry. When you want to download tiny little video applications on your cell phone, you want to make sure the footprint of it is very, very small. Because the devices can't handle it, and if the footprint is too long, it takes too many minutes to download. And as you all know, painfully aware, you pay for every minute to these carriers, right? You don't want to give them an excuse to charge you any more than they should. Okay, so the next technique that I'm going to talk about is what's called overlap save. Okay. And the basic premise of overlap save is the following. Let's just do a thought experiment. Okay, suppose I have x1, which is an L-point sequence, and suppose I have x2, which is a p-point sequence. When I convolve x1 and x2, I get an L plus p minus 1 point sequence. We all know that. And I'm assuming that L is much larger than P. Okay? So the correct way of convolving these two things is pad with zeros and then multiply, pad with zeros to get L plus P minus 1 point sequences or longer. Multiply the two L plus P minus 1 point DFTs. And then take an L plus P minus 1 point inverse DFT. That's the kosher or the correct way of doing all of that, right? Now, the thought experiment is as follows. Suppose we make a mistake of not taking L plus P minus 1 point DFT. You just take an L point DFT of this guy and take an L point DFT of this one. Because L is much, much larger than P, right? Taking an L point DFT is almost like L plus P minus 1 point DFT. In other words, L and L plus P minus 1 are almost the same number, but not quite. For example, if L is 1,000 and P is 5, in one case you're taking 1,004 point DFTs, in the other case you're taking 1,000 point DFTs. So you might say, well, they're almost the same. So what I want to do in this thought experiment is to figure out how much error and where an error is introduced if I take an L point DFT instead of L plus P minus 1 point DFT. So suppose that I take L point DFT of x1 and x2 and then multiply those. I'll do the same things as I was doing before. And then multiply the two L point DFTs, and then take an inverse L point IDFT. Take L point IDFT. So suppose I do this. What goes wrong? How many of the final L points that I'm going to get in this process are going to be garbage, are going to be erroneous, because I didn't pad with enough zeros, and how many points are not garbage? And the answer is, I'll first give you the answer, and then I'll try to convince you that that's the case. So if I do this thing, the real convolution will go from 0 to L plus P minus 1, and here I'm just taking L point DFT. So the answer is that the first P minus 1 points are wrong. So what goes wrong? And the answer is, we can show that only the first P minus 1 points are wrong. The rest of them are correct. And so let me try to sort of convince you with some sort of pictures that that's indeed the case. Okay? So why? And here's some sort of a sketchy proof, sketchy illustration, really, rather than proof. So suppose that here's my sequence as a function of n. Here's x1 of n. And suppose I have a sequence that goes all the way to here. It starts at index 0 and goes all the way to index L. That's my long sequence, right? L is much larger than p-type sequence. And it's got these points. These are the discrete samples of it. Okay? And suppose x2, which is the little tiny little p-point sequence that we're convolving with, this is the sort of a filter, has just 4 points. 0, 1, 2, 3. Okay? So what am I doing if I'm doing L plus P minus 1 circular convolution of these two guys? What I'll do is periodically I'll pad this guy with P zeros here, with a little bit of zeros, and then I periodically repeat the whole thing, and then I do the convolution. Then I do the circular convolution. So periodic, I'm going to draw this thing twice. So if I do L plus P minus 1 point, I add 4 zeros here, and then I'll repeat this guy here, where I have 1, 2, 3, 4 zeros. And then I start doing circular convolution of this with that, which would mean what? Which would mean flipping this guy over, 1, 2, 3, 4, right? This is x2 of minus n. And then I'll start multiplying, like this would be 0, minus 1, minus 2, minus 3, and then I'll start multiplying. What do I multiply? I multiply this guy by this guy. I multiply this point by this 0, this point by that 0, and this point by this other 0. Okay? I'm sorry, if I'm L plus P minus 1, this is 4 points, so there's 3 zeros that I add. My apologies. Bare minimum number of zeros you need to add is 3 zeros. So 1, 2, 3. Okay? I just made my zeros bigger. Okay? So here P is 4. I have to add 3 zeros. Here it is 1, 0, 2, 0, and 3, 0. And here is 1, 0, 2, 0, 3, 0. I repeated it, and I want to do circular convolution, and I multiply this point by that point, this point by this 0, this point by this 0, this point by this 0. And boom, the answer that I get is this, for at least this index, for index 0, is just the correct answer of linear convolution, right? That's how DFT was able to do linear convolution. We padded with enough zeros so that these guys, if I didn't, so that these guys don't interfere with the convolution, so that the answer is a linear convolution. And then I would just think of these as being attached like to a string, and then I click it by one index, and then this gets multiplied by the next one, this by this, this by that, this by that, and the linear convolution goes on happily. That's if I padded with 0, right? A review of last time's lecture. What if we didn't pad? So this is padding with zeros. What if I didn't pad this with 0? Then what would happen? Not padding with zeros now. Not padding with zeros, I'm just going to do an L point DFT. And so how would that look like? Well, the same picture. It goes all the way to L, and I have these guys. Okay? And now I'm going to get a replica of this, right, like just like this. I'm going to get okay, there's no padding here. This is index 0, this is minus 1, minus 2, minus 3, all the way, right? So if I don't pad it with 0, then x1 of n, which is periodic-wise, it's going to look like that. Now I have x2 of n, which is the flipped version of that, and to compute the index 0 of my answer, what do I multiply by what? Well, I'm going to multiply this point by this guy. Then I'm going to multiply this point by this guy. Then I'm going to multiply this point by this guy, and this point by this guy. And that's what my answer at index 0 is going to be. And is that, if my goal was to achieve linear convolution, would that be the correct answer? No, because of all these interferences from this tail end of the guy. Previously, I padded it with 0 to annihilate that interference. Here, I got this junk sitting here, and it gives me the wrong answer, so wrong. How about for index 1? Well, for index 1, I'm going to just drag this x2 of minus n by one index to the right. So how would that work? Let's plot that here. So it would look like this. Okay? x2 of 1 minus n. It looks the same as before, but it's just been shifted by 1. So previously, it had 0, minus 1, minus 2, minus 3. Now it's going to have indices minus 2, minus 1, 0, and 1. Right? So let's plot that. So it have 0, 1, minus 1, minus 2. 4 equal values. Just like that. This is x2 of 1 minus n. And so to compute, because there's 1 here, that's going to help me compute the answer at index 1. What is the answer at index 1? Well, it's the same thing. It's this guy multiplied by this, which is good. This guy multiplied by this, good. This guy multiplied by that, bad. This guy multiplied by this, bad. So the answer we get is garbage again. So for index 1, it's wrong as well. For index 2, it's the same thing, but I'm shifting it by one more time. So how would that look like? It's this thing, but the indices will be minus 1, 0, and 1, 2. So it will look something like this. This is x2 of 2 minus n. So it'll have minus 1, 0, 1, 2. 1, 2, 1, 1. So do the same thing. What's the answer like? So it's this guy times that, which is garbage, this times this times this, plus this times that. But because this guy is still spilling over, the answer is wrong. Finally, when I go to the last thing, which is x2 of 3 minus n, I'm going to do one last folding of the paper. If I now plot as a function of n, x2 of 3 minus n, that's 3 shifts of this signal, x2. So first shift, it moved, the last index was here, the second move was here, the third move is here. So now I'm going to have these 4 values, 0, 1, 2, 3. And now, there's nothing to multiply these guys. So the answer at index 3 is this times that, plus this times that, plus this times that, plus that times that, which is exactly what linear convolution would have done at index 3 anyway. Right? There's no more interference from these guys. So this one is good. Let's put a black dot saying it's good. And now, as I drag this thing to the right, it's just the same good linear convolution. There's no interference from these guys, and I get good answers all the way to the end. Good, 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 all the way to the end. So these are all good. So what I try to prove to you is that only the first 3 samples, in this case p-1 samples, were garbage because I chose to do an L-point circular convolution or L-point DFT. It resulted in repeating this thing without padding it, so these are the interfering guys. Is that clear to everybody? Okay? So I hope that I proved my point, which is this thing here that I wrote here, is that only the first p-1 points are wrong. Question?
Won't you allow p-1?
No, it won't. Let me just try to prove it to you. So for the last one, it goes all the way to here. Okay. Yeah. So by the time this gets, so we get 1, 2, 3, 4. That already gives you the Lth point. Okay. So look, when the 0th index of this is here, it's giving you the wrong 0th answer, right? How many shifts do I have to do for that point to get to the L point? L shifts, right? So all the way when I get to the point where this index is L and this thing, well, this is L minus, it's L minus 1 really, right? So all the way, so at this point, I multiply this by that, this by this by this, I still get the right answer. And that's really all I'm claiming. I'm not, you're right, by the time I shift that over one more, things go wrong again. But I'm saying of the L points that I get, I'm not saying of the L plus P minus 1 point that I get. What I'm claiming is that the L points that I get, only the first P minus 1 are garbage. But these I'm not getting at all. Okay. So having sort of shown that a little bit, what is my proposal for doing? What is my proposal? That's actually, I'm glad you brought that up. So what is the, having shown that only the first P minus 1 is wrong, what is a good scheme to take advantage of this thing? Well, the idea is to start segmenting your original sequence into L point segments, and then take L point DFTs of it. Then the answer is always wrong the first P minus 1 point. So what can you do to combat or to overcome or to undo the fact that the first P minus 1 points are wrong? What you can do is overlap the segments so that the first P minus 1 points here, for example, is computed in the previous one rather than the next one. So what do I mean by that? So here is the idea behind overlap save. What I mean is segment your sequence into L point pieces or L point chunks again. Okay, that overlap with each other by P minus 1 points, because that's how many points are garbage. And so what do I mean by that? If this is my long sequence, here's one chunk, for example, that's L points long, okay? And I know that the first P minus 1 are just garbage, okay? So then in the next chunk that I pick, however, the last P minus 1 points here is good. So the next chunk that I pick, I'll do it like this. I overlap by P minus 1 points here, and I know the answer I get off of here, the first P minus 1 are wrong, so I discard those and I keep these. And then the same thing here. I overlap by P minus 1 points. The answer I get off of this convolution, the first P minus 1 are wrong, so I throw those away, but I keep the last of these. But this whole thing is only L point long. Okay, this chunk is L point long. Okay? So in anticipation of the fact that this chunk is going to give me wrong answer for the first P minus 1 answers, I incorporated those P minus 1 points into this guy, into this L point chunk. And the same thing, in anticipation that this L point chunk is going to give me the first P minus 1 answers it gives me is wrong, I'm going to include that in this L point chunk. These are all L points. Okay? So step 1 is segmented into L point chunks, but they overlap with P minus 1 points. And then step 2 is you want to take L point circular convolution of each chunk. So what we want to do is, multiply L point DFT of a chunk by L point DFT of X2, which is our filter, and then take inverse DFT, take L point inverse DFT of that, and you get L numbers. And then step 3 is throw away the first P minus 1 point of the answer in part 2. So throw away the first P minus 1 points of the answer in part 2. And then replace it with the replace that answer with previous segment. Because the previous segment, its last p minus 1 answers are correct. Coming back into this picture, the last p minus 1 answer that we get from this chunk is correct. So we can bank on the previous segment to give us those p minus 1 points, and then the new segment, whatever answers it gives us as the first p minus 1, we just throw it away. Question?
In the diagram, where's the zero index for the input?
In this diagram, I didn't draw it, and that's a good point. Your question is, how do you do the first p minus 1 point of the first chunk, right? You have to do it by hand or do a special exception for that. Okay? That's a very good point. Yeah.
You do L plus P minus 1 for the first and second.
You could do L plus P minus 1. But again, you know, we haven't gotten to FFTs yet, but many times when you have an FFT routine, if you want to optimize everything, you don't write a general routine that does an arbitrary point FFT. You fine-tune it to be a power of 2, or you even fine-tune it to be like 512, but you want to have efficiency in your code and all that. So, but you do have to do something different for the very beginning. Okay, is that concept here clear? Let me. There's a nice picture that I want to show that illustrates this a lot better than I can draw, just so that there we go. So any questions on this? Okay, so let me now show figure 823 of Oppenheim and Schaefer. Here we go. So rather 824. So 823 shows the overlap and add. Okay. So here we divide the sequence into L points chunk. Could you maybe? Yeah, great. L points chunks. Here's one. Here's another. Here's another. X1, X2, X3, and then we convolve the first one. We convolve this L point chunk. Can you zoom out just a tiny bit? Actually, zoom out so that the whole picture is shown. Great, thank you. So here's the first L point. Here's the second L point. Here's the third L point. So then you convolve this L point with a P point sequence, and you get this convolution, L plus P minus 1 point answer. Then you convolve this second chunk with the P point sequence, and what you get is this chunk. And you convolve this with the P point sequence, you get this chunk. So there's an overlap between the non-zero answers here and here. So you add these guys up for the final thing. You add these guys up here. We're just doing overlap add, and you're strictly speaking just taking advantage of the convolution, the associative property of the convolution. Okay. Now overlap save, which is this second concept I talked about here, is shown here. And if you can zoom out just a tiny bit, great. So here's your L point sequence, okay, and and when you yeah, so here's an L point sequence. Here's another L point sequence that overlaps with the top with X0 with P minus 1 points. Why are we doing that? Because we know that the answer that these guys give us, the first P minus 1 is wrong. And here is the second chunk of the sequence, X2, which again overlaps with X1 by P minus 1 points. So that's how you divide up your sequence into chunks with P overlap between them. And then you come down here, you do the convolution with the H filter, with the 3 or 4 point H filter, and the beginning answers are wrong, you throw those away. The same thing here, you throw that away. And the same thing here, you throw this away. And now you add all these things up. And the good thing is that because you throw this away, for each index here, you're adding these up to 0 or to nothingness. So you don't really, the answer at each point of the final output only depends on one of these guys. In the previous case here, I had to add up this to that, right? They were overlapping non-zero values. Here, there's no adding up to be doing. Okay? All right. Any questions or comments on this? Okay, so it's a pretty straightforward concept, and I think I'm not sure. Do you guys have a homework problem on this? Yeah. Okay. All right, that should clarify things a little bit more. So in the remainder of today's lecture, what I'd like to talk about is the discrete cosine transform. And I realized when I did DFT, I promised that would be the last thing I'll introduce in the course, but I'm breaking my promise, and I would like to talk about discrete cosine transform simply because it's one of the most widely used transforms in that almost all image processing standards are based on DCT. MPEG-1, MPEG-2, MPEG-4, H.264, which is the new thing after MPEG-4. They all use discrete cosine transform. And I sort of want to motivate and tell you why there is a need for a new transform. Okay? And then I'll talk about what it is, and then I'll talk about its compaction properties and show you that it does something better than DFT, and that's why people use it. So this DCT, or discrete cosine transform. Okay? So it has two properties. One of them is compaction property, and I'll talk about that in a second at the end of the lecture when I show you some pictures. So it's compaction property. Okay, and the other thing is that the coefficients end up being statistically independent of each other. So let me explain what I mean by that. So if I have an image and I want to be coding it, and you'll learn a lot more about this if you were to take EE 290T next semester, which is a grad level course I'm teaching. By the way, the prerequisite for that course is just this course, EE 123. So if you want to learn a little bit more about image and video and how to push video through networks and all these other things, do take the course. But let's say you have an image and you want to be compressing it and you have a whole lot of pixels on it, right? One way of compressing things or code things is in the pixel domain. You know, you can just quantize. You say each pixel is 8 bits. Oh, I'm just going to throw away the least significant bits of it, the 3 least significant bits, and make it 5 bits, and that's it. And you can become a little bit more clever. You say, I'm going to predict this picture. This pixel and this pixel are right next to each other. They probably correspond to the same object. So instead of coding each pixel independent of each other, I'm going to code the difference between them. Okay, and just keep going like that, for example. Or you can say, oh, why code the difference? I'm so smart. I can tell you, I can predict what this pixel in the middle is by looking at its neighbors that I've already coded. I do some sort of a weighted linear combination, or even nonlinear prediction. I'm so smart I can come up with really good prediction techniques. I predict this picture from its neighbors, and then subtract the prediction from the actual pixel, and then I come up with the error, and I code that error. That's the quantity that I quantize and code and all those other things. So these are all called pixel domain techniques. What DCT helps you with, so why are these techniques good, and how are they performed? They're taking advantage of the correlation that exists in the pixel domain between neighboring pixels, right? And no matter what prediction scheme you use, deep in the back of your mind, you're always wondering, could I have done better? Did I take advantage of all the correlation and all the, essentially all the correlation that exists between these neighboring pixels? Or could I have done a better prediction and therefore make the magnitude of this error signal, the difference between the prediction and actual, I call that the error signal. Could I have made the magnitude of that signal even smaller and therefore achieve better coding? So in contrast, there's another class, so these are called pixel domain coding techniques. There's another class that's called transform coding techniques. And what they do, for example, discrete cosine transform, they take a chunk of the image, let's say an 8x8 block of it, and then they take a transform of this and come up with another 8x8 set of numbers. They take 64 numbers in, 64 numbers out. And for all that you know, it could be DFT. I mean, for God's sake, we put a lot of effort before we reached the point where we could explain DFT, so it could be anything. It's a transform. And so you give it 64 numbers in, 64 number comes out. DFT is a perfect candidate as well. It could be DFT, DCT, or anything like. But now these coefficients, the good property they have, they're statistically independent of each other. They're no longer correlated. I can't predict this guy from its neighbors. Okay? I've ended the prediction game, and I've ended the uncertainty associated with prediction. Now I know that because my transform was a good transform, I have made my coefficients statistically independent of each other. And so I can stop playing the prediction game, and I can just code each one of these individually. You say, well, wait a second. Is that going to do better than this? The answer is not quite. And that's where the compaction property kicks in. The reason this is a good scheme is not only these are independent of each other, but there's also a compaction property in that of that 64 coefficients, I can keep the biggest 5 and throw away the remaining 59. And throw away, I mean set it equal to 0, the remaining 59. And if I take inverse transform of this in the picture domain, virtually I see no difference. That's called the compaction property. Okay? Which means that you can keep a very small percentage of the coefficients and throw away the rest. Of course, you do see some blurring if you throw away 90% of the coefficients or 95% of the coefficients, but for most practical purposes, so depending upon how much bit rate you can afford and what fidelity you want to get, you keep more coefficients or fewer coefficients. So the reason for doing transform coding is these two things: is that the coefficients in the transform domain are statistically independent, and they have the compaction property. So and so you might say, well, why use DCT? Why can't I use DFT? And I'll explain that in just a second. So before doing that, let me just tell you a little bit more about DCT. DCT is used in JPEG. It's used in MPEG-1, MPEG-2, MPEG-4, H.261, H.263, H.263 plus, H.263 plus plus, and then H.264, etc. So it's used in all of these things. The first and only non-DCT based standard. These are all standards. People come up with standard schemes for video devices to be able to communicate with each other, right? Like my picture phone is going to take a picture of something, and let's say I'm a Verizon subscriber, which I'm not, but suppose I am, and I want to send it to I don't know, Kevin, who is a Sprint subscriber. If there's imaging standards like this, then if I encode my picture in one of these standards, then his phone is going to they're all retrofitted, let's say, with JPEG. When I send my picture to him, boom, he can actually view it. That's the beauty of having standards. All right. So DCT is used in all these standards, and what is the first standard that did not use DCT? Which means that I have to teach you yet another transform, but I might spare you of that. But what's the first standard image coding technique that did not use DCT? Anybody? It's called JPEG 2000, and that used wavelets. Okay, so other than the answer is other than JPEG 2000 that uses wavelets, every other image/video standard uses DCT. And one of the questions you might ask is, can we not apply wavelets to video? The answer is nobody has been able to prove that. Even the wavelets have been around for 10, 15 doing motion compensation in the wavelet domain is difficult, and I just leave it as that. I think it's too hard to get into the details of it. But there's other fancy video techniques that you can use. You have to understand, actually, the discovery of wavelets is a pretty exciting thing in the signal processing community. Why? Well, it was invented like in 89 or 90 time frame, and it was invented by 3 different communities. There were signal processing communities that were doing filter bank stuff, and then there was the computer vision community that was doing what's called multi-resolution stuff, and then there was the harmonic analysis community. That's the applied mathematicians. I think we have one applied math major here in this class. So they sort of all independently came up, or maybe in collaborations came up with wavelets. In computer vision, Stéphane Mallat was the person who did that. It turned out, he's a French guy, it turned out he was going out with the daughter of Yves Meyer, who's a geophysicist in France. And then in talking to his girlfriend's father, they had been using these things called wavelets in geophysics for years. So then he applied it to his PhD thesis at UPenn with Ruzhnabachi, and then that resulted in a major publication. Then at this end, then when it was published, then the signal processing people said, "Oh no, that's nothing but filter banks. We already knew about filter banks. That's not new." But in fact, it went beyond filter banks. So. And then in the harmonic analysis domain, this Belgian woman, Ingrid Dauberchet, who's also French-speaking, introduced wavelets and other things. So most of the early literature in wavelets, it was in English, but it was produced by French-speaking folks. So here's Dauberchet, which I have a very hard time spelling her name. She's now at Princeton, by the way. And Mallat used to be at Courant in New York, Institute of Applied Math. He's back in Paris. I forgot which university. École Polytechnique Supérieure. That's a very long name. The French are known for these impossible long names. Do we have any French students here? No. Okay. And the filter bank community, I guess Verily had been working on that, and from the 80s they had been applying filter banks to speech signals and to images, and then it turns out that there's also a link from that to wavelets. But why is it wavelets important? I mean, I won't get into the technical stuff. Maybe this is the topic I'll talk about in the 1 or 2 lectures we have extra at the end. Just to put it in perspective, if I put aside wavelets, almost all the Fourier analysis stuff that I taught in this course, and you learned in 120 and you learned in 20, was invented by Fourier in, I don't know, 1700 something, 1800. What century was Fourier? 1800 or 1700? Yeah. So it's at least 250 years old, right? So it's not every 5 years that such a fundamental new thing gets introduced. This was introduced in late 90s. So we are sort of living at a particularly exciting times, right? I can imagine, what year are we now? 2003. I can imagine like my great-great-great-grandchild will be teaching this course, probably, hopefully not in this room, but somewhere nicer. And they say, oh, wavelets was invented 250 years ago. This is 2,250 or something. And 250 years before that, Fourier invented Fourier analysis, right? So the last time, so if it wasn't for wavelets, almost everything I taught you in this course is 200, relates to stuff that's 200 years old. Yeah. Oh, just one sentence description of it. I think I wouldn't do it justice, but it's from a signal processing point of view, it's a way of looking at the signal at multiple resolutions and convolving it with a set of basis functions that are related to each other that enable you to see the signal at different resolutions. It's almost like having a magnifying glass and looking at you in a blurred way first, and then decrease the blurring function, and I look at something sharp and sharper and sharper and sharper. It's a multi-resolution, multi-scale representations of signals. I think I'll try to make sure that talk about filter banks and wavelets at least for half an hour at the end of last time's lecture. But anyway, other than JPEG 2000, this was supposed to be a lecture on DCT, so we shouldn't get off track talking about wavelets. But let's move on to DCT. So I will talk about this aspect of wavelets, this link, because we're signal processing people to wavelets at the last lecture. So here's so how does and one other thing I want to say is besides DCT, there's like a whole lot of other transforms. There's Hard, there's Hartley, there's Hadamard. It's really an accident that they all start with H, but Walsh, you just name it. There's lots of things. So how does DCT work? Well, and how does it? What's one motivation to study DCT? Well, DFT, if I have a real sequence, outcomes in X of K, which is a complex sequence. It is conjugate symmetric for sure, but it's still a complex sequence. DCT, I given a real sequence, and outcomes a real answer. So that's already one advantage. But why DCT? Okay, and who figured out to apply DCT to images and video? That's 50 years old. Okay, so if you think about DFT, you start with X of n, you make the signal periodic, and then you take the discrete Fourier series of it, which is X tilde of K, and then you take one period, and that's DFT, right? Which is X of K. And this thing here, the discrete Fourier series, it's expansion in terms of exponentials, e to the j 2 pi n k over n's. 2 pi k is over n's. Okay. And so pictorially, how is this thing working? Well, if X of n, most signals are locally smooth. Let's say X of n looks something like this, right? When I go through this chain and I take the discrete Fourier series of it, I'm taking discrete Fourier series of this signal, right? I periodically repeat it, and I'm not taking discrete Fourier series of that. I'm expanding this periodic signal in terms of these exponentials, right? And why is that problematic? Well, the value for the last point here and this point get to be neighbors with each other. And in typical sequences, let's say I take a picture of this room, and on the left-hand side is let's say Kevin, and on the right-hand side is Alan. Is there any guarantee that the rightmost pixel for Alan should correspond to the rightmost pixel of Kevin? No, they're two different people. Is there any guarantee that this pixel should be the same as that, or this pixel should be the same? No. Because DFT has forced me to periodically repeat that, and now I have to take DFS of it, and here there's a sharp discontinuity. And what is a sharp discontinuity? Intuitively speaking, what does a sharp discontinuity do to the harmonic coefficients of a sequence like that? It gives you what if you have sharp discontinuities? It gives you high frequencies. Unnecessarily. Okay? It's only here because I chose to replicate this sequence in this manner. And what DCT does, it says, let's not do that. Let's replicate this in a slightly more clever way. Let's flip this over like that and then do harmonic analysis. That way, this point is next to itself, and everybody is equal to itself. So I'm not going to have this sharp discontinuity, and therefore I'm not going to have this jump. Okay? So the basic idea behind DCT is to replicate the signal in a better way so that there is no sharp discontinuity. Okay, so in particular, if I have a signal like this, x of n, then the way this thing does it is like this. It'll do 1, 2, 3, 4, 5 like that, and then it repeats that. It mirrors it. It mirrors the signal back. So if x of n looks like this, then maybe we should do a DFS of this mirrored signal. You know what I mean by mirrored? I'm just flipping this over like that, this, like that. And so if this was alpha, alpha 1, alpha 2, alpha 3, alpha 4, alpha 5, this would be alpha 5, alpha 4, alpha 3, alpha 2, alpha 1, and then alpha 1, alpha 2, alpha 3, alpha 4, alpha 5. So in the analogy here is the leftmost pixel corresponding to the edge of Alan's face equal to the leftmost pixel corresponding to Alan's face? Yeah. There's not going to be any sharp discontinuity. So from here to here, no sharp discontinuity. In fact, you're sort of extending it with least amount of change. Okay? So that's sort of the basic idea, and I'm going to now talk about the formal definition of DCT. There's actually 4 kinds of DCT. There's DCT1, DCT2, DCT3, DCT4. It's just because signal processing people couldn't get along couldn't agree with each other, which should be called DCT, so they have 4 of them. But for this course, I'm going to talk about only DCT kind 2. So we'll focus on DCT2, okay? And the basic definition of it is as follows. X, I'm calling it C2 of K, which is the coefficients of it, is 2 summation x of n cosine. I'll come back to this picture a little bit more, and first let me write down the mathematical equations, and then I go back and relate to this symmetric flip that we just did. Cosine pi k 2n plus 1 over 2n, and this goes from n equals 0 to n minus 1. And this is the analysis part. And the synthesis part, which means how to get back x of n from the coefficients, is like this. You get x of n is 1 over n summation from k equals 0 to n minus 1. And there's this thing beta of k, and I define what beta of k is right here. It's half for k equals 0, and it's equal to 1 for k between n and 1. So beta of k cosine pi k 2n plus 1 over 2n. Okay, the whole thing. So that's sort of nice. Forward DCT and inverse DCT, you can use the same function, right? Talking about the size of application or the size of code or the size of executable not getting too big, you can do the exact sort of same thing. And so now what I'm going to propose, and maybe I should really do this on Friday's lecture because there's like way too many pages. Yeah, I'll just write down the proposal and then I do the proof. No, let me, yeah. I'll do the proof on Friday's lecture. So here's the relationship from DFT of x of n to its DCT as defined in the previous page, DCT page 2. So the proposal is this. You start with x of n, okay, which is an endpoint sequence and it's real. And then you take a 2 endpoint DFT of it. And how do you take 2 endpoint DFT of it? You pad it with 0, yeah. Mm-hmm. Oh my God. Thank you. There is no... Jesus Christ. Thank you, Dan. There's a x. These are the coefficients for which we're taking. Otherwise, there will be, no matter what sequence you... no matter which DCTs you always get the same sequence back. Okay, xc2 of k. Thank you. All right. Actually, you know, that reminds me, that's the kind of bug you get into your software. You spend all night for your homework doing this assignment, and you apply the inverse DCT, and you always get the same answer. You say, what happened? Oh, I forgot to put this. Okay. All right, so here's the proposal. You start with an endpoint sequence, you take a 2 endpoint DFT of it, and you get a new x of k. And then you take twice the real part of x of k times e to the minus j 2 pi k over 2n. So that's one way of doing it. That's proposal 1. I'll prove that next time. And proposal 2 is this. Step 1, you start with an endpoint real sequence, x of n, and then you pad it with n zeros to get a new sequence, x up to n of n, I call that. And then I form a periodic sequence, which is x2 of n, which is just x tilde 2 of n plus x tilde 2 sub n minus 1. This is the flipping over that I was talking about. Okay? It's you pad it with zeros and then you add it with that. That's equivalent to, where's that picture now? I lost it. Page 14. No, page 13. Oh, yeah. That's the equivalent of doing this flip. And I'll talk about that. I'll convince you of that next time. And then the next step is, step 4, is take the 2 endpoint DFT of one period of x2 of n tilde. And that's x2 of k. And then that we relate to DCT. So those are 2 ways that DFT is related to DCT, and I'll prove these on Friday's lecture. Okay, and then on Friday I'll also start talking about FFT, so that you know all the material you need for the next homework. Okay.